Okay, something that I would love to discuss and share with you is the linear systems theory. And this is something that we're going to start on this video. So let's let's start a discussion about linear systems. And since this channel, its purpose is about robotics and also control theory and its applications. So you're going to see that linear system uh, is very related to robotics and control theory. And also something that I would love to discuss with you in the future is about dynamical systems, and it's going to be very useful if we construct a knowledge about linear systems first. So we're going to start to discuss about linear systems, and the book that I will be using to make this series possible is Linear System. It has the same name, so Linear Systems Theory. And the author, its name is João P. Espenha, I think is that way how we pronounce his name. And this book is very nice to start with this content. And the author, João, I think it's Pedro, I don't know. Espanha. Okay, and hope it doesn't have any problem in using the content of the book, and other rights is reserved to the author, of course. And okay, so let's start with the chapter 1, which is about state space linear systems. So the contents, uh, let's develop the content as we pass throughout the lessons. So first of all, we're going to start with the allosaurs of linear system, with the base, which is state space linear system. Okay, first of all, let me explain to you what is the meaning of state space in linear system. So space state is a mathematical representation of a dynamical system. Now I force it to give to you the meaning of a dynamical system. So now a dynamical system is basically how something evolves over time. How something evolves over time. And I can give you some examples. So, examples of dynamical systems. So, for example, we have a swinging pendulum, a weight in a road swinging back and forth under the gravity, and this is changing its position and speed continuously. We also have the planetary motion, the orbits of the planets moving around the sun due to gravitational forces. We can have a bouncing ball, a ball dropped on the floor repeatedly hits the ground and loses height and bounces in discrete steps. And dynamical system is something that we can apply in the nature in so many different problems and examples. A car on the road changing its velocity, its acceleration, so it's going to change the position. The position is not going to be continuous in the way that the velocity change also can be gradually increase or decrease. So a system that it changes over time. And the key concept when we are talking about dynamical systems is state space, which is I'm explaining to you right now, is very related to dynamical system. And now you know that a space state space is something that is a mathematical representation, is a model of a dynamical system. So when we are discussing about dynamical system, we are tied to the concept of state space, the time, in a evolution rule or a model. Okay, and I still can give to you a better description of these key components, key concepts. So these are key concepts when discussing about dynamical system, dynamicals or dynamics. So again, state space is a way to represent mathematically a dynamical system. So is the set of all possible values or positions that the system can take or assume. And of course, when we are discussing about something that involves with time, so the time is a very important concept, is a key concept. So is how the time is measured. Which can be continuous or discrete. So it can be continuous or discrete. And this is will depend on the problem that we are working on it. And another important key concept is the model or the evolution rule of the system. And we can tell that is a mathematical function which is often, most of the time, a differential or different equation. Differential or difference equation. And we can say that this is dictating the dynamics of the system. So it dictates how the current state moves to the next state. Okay. So now let me also explain to you what is a linear system. So I explain very quickly, and of course I will give you more examples, and this is something that we can is indispensable to the introduction of the mathematical models that we will be discussing throughout this video and also throughout all the theory of dynamical systems. Sorry, the theory of linear systems. So now let's see what is linear. And this is, we will have a mathematical description also. So if you Google about linear system, you will see a definition very similar to this. Is a linear or pretty much the same. Is a linear system is a set of two or more linear equations that shares the same variables. And must be solved at the same time. Now, it is very important to let clear also what is linear. So let's also see the definition of linear. So what is linear? So this concept, it got two key concepts also, which is additivity and homogeneity. Homogeneity. So first, let's see what is additivity. And then what is homogeneity? Sorry, homogeneity. So additivity is when we give a certain input to a system and we'll give in return a output equivalent to this input. So if an input x1 gives an output y1 and an input x2 gives an output y2, then adding the input x1 and x2 gives the exact sum of the outputs y1 and y2. Now, to be linear, it also needs to be homogeneous. So the property homogeneity and that is something that we study when we are studying differential equations. So this is something that we study when we are into differential equations. So right here you will see that not only dynamical system but also linear system, which is the focus on the series that we are about to develop. So this concept is even more simple. So if you multiply an input by a constant, number, for example, like C, the output will also be multiplied by the same constant. So for example, if we have a system, any system, and we got the input and the output, and if the inputs we are applying any variable, let's say x, and on the output we will get this y variable, and if this system it multiplies this constant, it multiply this input by a constant c, so the output it will be that constant multiplied by the input variable. Okay, and we got this other example. So now using a differential equation, so how x evolves over time if a respective time, so a constant and a state. So now x of t is the state, and given a variable u, which is the input variable, and when we are using this dot above the x, is the same as the derivative of x, which is dx over dt, dx dt. Okay, now let's get back on track. And now the content that I will introduce to you is from the book. So we will start with continuous time state space linear system. So continuous time so we have continuous and we have discrete. continuous time state space, linear system. So a continuous time state space linear system is defined by the following equations. The following two equations. So x dot of t, which is the derivative of x in respect to t, is equal a of t times x of t plus b of t times u of t. And the output equation, which is y of t, which is equal c of t times x of t plus d of t times u of t. And this is with x on the r to the n and u to the r belongs to r of k to the k, and right here on the output equation with y, which is belongs or is on r to the m. Now let me write what each term on this equation it means. So x dot is, so x dot of t is the state vector y we don't need the time right here. But as you can see, it is in respect to the time, so time is the variable that governs this dynamics. And y is the output vector and u is the input or control vector or variable. I prefer variable. So the input variable or control variable but also can be a vector. A, which is a state or a system of matrix of values, so is a matrix. State or system matrix, and B is the input matrix. C is the output matrix. And as these are matrices, so the dimension right here is n by p and q by n. Sorry, right here is n by n, the dimension. Right here is n by p. And right here the dimension is q by n. And now D, which is the feed-forward matrix, and its dimension is q by p. Okay. Now let me also introduce some terminologies in linear systems. So terminologies. In linear systems. So a single input or with the abbreviation SI is when the input signal or the control variable U takes scalar values for example k equal 1, or it can be k equal 2, 3, and we also got multiple inputs. with the abbreviation MI, which is when the input signal you assume multiple values. Another terminology that we will be using with very often is LTV, which is linear time variant. Sorry, linear time varying. And linear time invariant. Which is abbreviating LTI. In all this, we will see as we pass through the lessons of the book. So I don't need to speed up or hurry up this with you. Okay, so this is just the introduction. And all these concepts, they are key, they are very important for the development of the equations, of the problems that we are about to solve, to discuss, to understand. And now we will start with block diagrams, which is a convenient way to represent systems. And these block diagrams generally serves as a complex representation for complex equations. So we already I already introduced a system and with this representation using blocks. So you can represent any system using a block diagram, and right here we will call these blocks as P or P1, P2. So a block diagram P, and we got on the input a control variable U, and let's just use U on the input, and on the output W. Okay, but this we will discuss on the next video. For now is all. So on the next video we will start with block diagrams. And we will discuss about interconnections. Okay, so for now is all. Thank you for watching. Hope you follow along this series that we are about to develop, and it's going to be nice if you leave the like, if you subscribe to the channel, and feel free to criticize and do comments. Thank you. See you in the next video. Bye bye.